So in the last class we discussed about the construction of BGR, and let me just try to get back the circuit. So our main idea is to use two different structures with diode connected, and let us assume that the emitter area of this first transistor Q1 is said to have an area which is AE, and its collector current is given by something like I naught, and we also have a second branch of circuit where it is again passed through not just the diode connected structure, but we also passed it through a resistor carrying a resistance value of R1, and then which is then passed on to an NPN transistor with an area which is n times greater than the area of Q1. Okay. So now that when we tap these outputs, for the first structure, let me have a label as VO1, and for the second structure, let us label it as VO2. Now, this particular structure generates basically the VO2 is said to have this V reference. Okay. Yeah. So this could have a value of V reference provided if the current that flows through the circuit, if it is labeled as I, or basically the I naught. Now, so that has been multiplied with R, and we have to generate a VB out of this. So let me write it as VB2. Okay. So now this VB2 contributes to negative temperature coefficient component, but we want to have a positive temperature coefficient out of this combination of I naught into R1, right? Yeah. So in order to get that, one has to ensure that the potential of VO1, if it been made exactly equal to the potential across VO2, then one could replace this combination of I naught into R1 with a value which is, yeah, I think Vt ln of n. Okay. So this combination of I naught into R1 could then be replicated as something like this quantity, provided if I could able to satisfy this relation. Okay. And then we have this VB2. Yeah. So, and in this case, we have assumed that the factor of alpha 2 as well as the factor of alpha 1 both are considered to be equal to 1, and that is how we have this. And in such situation, what happens is that the ln of n factor supposed to be approximately equal to 17.24. Okay, so that is what the requirement is. And later what we did is that we imposed on two mechanisms. One has to ensure we need a mechanism that guarantees the relation of VO1 to be exactly equal to VO2, and the second type of thing is that one has to ensure this ln of n to be equal to 17.24, and this in turn actually translate to a large value of n. Okay, and that value of n is almost closer to 30.7 mega. Okay, so that is the large area that is required by the second structure Q2 in order to achieve this V reference across this node V out, VO2. Okay. Now, in order to there are some alternate way by which one could ensure these two conditions, like the first condition being VO1 to be equal to VO2, and trying to dilute this large value of n into a small value. There were two kind of circuits that one could use in order to build this BGR. Okay. The first circuit was built by realizing this current I naught across both these branches with what is known as supply independent biasing circuit. Okay. So we use this biasing circuit in order to ensure that our I naught across both the branches to be same. So say for example, if I label this I naught that is flowing across the branch number 1 as IO1, we want this IO1 to be exactly equal to the current flow across this IO2 as well, or across the second branch as well. Okay, so we achieved this by doing some small modification onto this supply independent biasing, uh, and yeah, and also one has to ensure this VO1 to be equal to VO2. Sorry, I forgot to mention this. Okay, yeah. So now one could use a supply independent biasing in order to ensure this particular parameter value, but in order to ensure the main requirement of VO1 to be exactly equal to VO2, we need some modification to be done to this supply independent biasing circuit. Uh, so just as a recall, what we did is that we had ensured that the W by L factor of NMOS current mirror structure, we made them equal. Okay, so if we could make this relation to be same, then what happens is that one could ensure that the value of VO1 to be exactly equal to VO2. And based on this, let me quickly draw the structure, just because later we had stated about a particular problem. So in order to solve that problem, it is required for us to redraw the structure. So first let me draw the PMOS current mirror structure, and then followed by this we need an NMOS current mirror structure in order to feed the output to the input I reference, and at the bottom we tap the outputs of VO1 and VO2 across this source terminal of M1 and across the source terminal of M2. We observe that to be equal to VO1 to be equal to VO2. Okay, so just as a recall, the W by L factor of both this the transistor 4 and transistor 3, we made them to be equal. So this equality was meant to ensure that the current flow through both these branches, let me write it as IO1 and IO2. Okay, so we want both these currents to be equal. So this is the one, the combination of M3 and M4 current mirror having the same aspect ratio ensures that both the branch currents are equal to each other. So this is done already, but we had kept the W by L factor of 2 to be k times higher than the W by L factor of 1. Okay, so this was the requirement that we imposed when we discussed about bias independent. Uh, yeah, it's a supply independent biasing circuit, right? Yeah, so this was the case that we had in order to ensure that, but having a k value which is greater than 1 will not give us the requirement of VO1 to be equal to VO2. So this case leads to something like they become unequal. So in order to ensure that our VO1 to be exactly equal to VO2, one has to make sure that the k value is taken as 1, which means I have to have both the NMOS aspect ratios to have the same value. So that we equate to W by L of N here. Okay. So with that condition, one could ensure that our VO1 to be exactly equal to VO2. Yeah. And after this, the bottom structure remains the same. So whatever the structure that we had earlier, that is a diode connected across the branch number 1 or across our VO1, and a resistor in combination with this diode connected VGT across VO2 is what we need to plug in back. Okay. So let me try to reconstruct the same thing, and during this construction I changed this structure from an NPN transistor to a PNP transistor. So the reason here is pretty simple, just because in most of the cases the PNP transistor is more compatible with the CMOS technology, and that's the reason why we went for this Q1 being replaced from NPN to a PNP transistor. Okay. Similarly, one can also do the same thing, trying to replace this Q2 with a PNP structure. Okay. Yeah. So again, one has to ensure that this value of N is or the emitter area of this Q2 is higher than the emitter area of Q1. Okay. Yeah. So with that taken into account, we already know that having if at all, if you want to tap the output right away from this V out as your V reference, this V reference in turn imposes a factor of n that is closer to 30.7 mega. Okay, so that is a huge value that has to be incorporated onto the Q2 transistor. Okay, so now that we just don't want to have this particular relation, in order to alleviate this particular problem, we added an extra circuitry across this structure in order to ensure that this value is not going beyond a particular value of 5 or 10. Okay, so we don't want more than that. So we generally want to restrict the value of n to be small, which is lesser than the factor of 10. Okay, not like in terms of mega. And in order to have a value of n that is smaller, we have to add an extra circuitry along with this structure. Okay, so what we did is that let me try to move off these. Yeah. So what we did is just added an extra mirroring circuit where we tap the gate voltage of M4 and we feed it to M5 structure, and then the current flow through this device will be the same as that of our current flow through this IO2. Okay, so I would mirror the same current flowing across this M5 structure as well. Okay, now so what we have generated is just the IO2 value, but in order to know what is this exact value of this IO2, one could make use of this current flow through the resistance. Okay, now as we know that the drop across this resistance leads us to a value which is Vt into ln of n, right. So that is the voltage drop that we have across this R1, which mimics our PTAT circuit. Okay, so based on this realization of R1 as a PTAT circuit, we could write the drop across that resistance as Vt times ln of n, right. So now I know the drop, I know the resistance, and in order to measure the current flow, the only thing is to use the Ohm's law relation, which dictates that Vt divided by ln of n should get us the value of the IO2 value. Okay, so this is what we ended up having, and this current would then flow across this M5 transistor, provided if the aspect ratio of this M5 is same as that of all other PMOS transistors. Okay, so if I have this, then IO2 would be the same. Clear? Yeah. So having got this structure, we still need to have a V reference, because I cannot use this particular node VO2 as my V reference, just because if at all if I want to use, then I need an n value or a factor of n that is equal to 30.7 mega. Okay, so which means that quite a larger area for our Q2 structure, and we don't want such a large area to be incorporated onto our IC. So in order to eliminate this, while we try to eliminate this, then VO2 will no more mimic our V reference. Clear? So now that I somehow have to tap this V reference to be generated out. So what one can do is that one could pass this current to flow across this R2. So again this R2 would then try to mimic the same PTAT structure and pass it through the diode connected transistor like Q3. Okay, and the area of this emitter area of this doesn't matter here. The only thing that we are concerned is the generation of VBE alone. Okay, yeah. So in this case, I could have the same emitter area, doesn't matter. Okay, yeah. So now having got this, I have generated a VBE potential in order to have our V reference out of this Q3 structure. Okay, so let me write it as VBE3. And I also need a PTAT circuit to have a quantity here. Now in order to measure this drop across this R2 which mimics the PTAT circuit, I have to multiply the potential drop across this R2, right. So the combination of IO2 into R2 should mimic a PTAT circuit's realization. So now that we know that the value of this IO2 is directly plugged in here, which is nothing but Vt into ln of n, and that has been multiplied with R2, and the whole of this has to be divided by R1, and right now the combination of this R2 by R1 gives us a factor of alpha 2, okay. So which is no more uh, equal to 1, but rather it's a kind of number which is greater than 1, okay, and that has to be added with this VBE3. Okay. So this is how we could tap this output as our V reference, okay, provided if the value of n that I have across this Q2 is smaller, okay. So approximately to a range of value from 2 to 10, okay. So within that range if I have, then I cannot tap this VO2 as our V reference, but rather I have to pass it through one more structure which is a combination of M5, Q3 and R2, yeah, clear. So hope that it is clear, and this was being followed by a problem. Hope you people are remembering those problem. Let me, I think I have to check whether uh, yeah, so I think you have to design this BGR provided a specification was given, and since because I don't have the specification, the solution for the given specification, I will change the specification a little bit such that I have a solution so that I can work out for you, and then you can check it back by working out with the specification that I have gave in the last previous class. Okay? Yeah. So let me rewrite these parameters. Certainly these parameters have got changed a little bit. I think the supply voltage is equal to 3.3. I think this remains the same, and the DC bias current, okay, which is nothing but our IO2 or IO1, okay. So that current is said to have 6 microamperes, okay. So whereas in the previous class I gave a spec value of 5 microamperes, but I'm just going to change the spec from 5 to 6 just because I have solution for this. I don't have solution for 5, okay, and let me have an n value which is 2 for the PTAT generation, and the resistor values, yeah, so this was not mentioned. So whatever the resistors values that we are using like R1 and R2 supposed to have a value which is less than 50 kilo ohm, okay. So probably this spec I didn't give in the last class, yeah. So let us try to work out the same, and in order to realize this I am just going to use this circuit that I have drawn earlier. So let me just make a copy of it. Yeah. So now that we have done with it, and let us try to evaluate each of these resistors values of R1 and R2, okay. Yeah. So now let us assume that the value of VBE is equal to 0.75 volt, and now that we just want to evaluate the value of the resistor R1, okay. So that becomes pretty simple, like we know the value of n, and we also know that the drop across this R1 is given by Vt times ln of n, which is the PTAT circuit. So this is the voltage drop, and the current that is flowing through this IO2 was given from the spec, which is equal to 6 microamperes. So which is just the IO2, or in general I naught. Okay, yeah. So when we plug in those quantities here, uh, you would end up having a value which is equal to 3 kilo ohm. Okay, so you can just verify it just by plugging those values and then check whether you are getting the same answer. I'm just writing the final value here. Okay, and next we need to evaluate the value of R2. Okay, so whenever this question has been asked, you need to draw the complete structure and then you need to evaluate these quantities. Now, in order to calculate the value of R2, we have to make use of our V reference source. Okay, so or if at all if you know what is the drop, you can directly do it. Okay, let me do the other way. So the current that is flowing through this R2 resistor is given by the same I naught, and the voltage drop across this R2 is given by IO2 times that of R2. And now that we know what is this IO2, directly taken out from this expression, right? Yeah. So this value supposed to be equal to ln Vt into ln of n divided by R1, that gives me the value of the current flow of IO2 into the resistor R2 here. Okay, and this is the value that we want to evaluate it, and the combination of this ln of n times that of R2 by R1. Okay, so this combination should end up having a value of uh, 17.24. Okay, and this is what we wanted out of the circuit. So somehow we need to constrain the value of this entire quantity of ln of n times that of R2 by R1 to 17.24 value. Now based on this constraint, one could evaluate the value of R2 here. Okay. So again, plug in the value of ln of n, which is 2, into the resistor value of R1 is already known, which you can plug in here, which in our case it is 3 kilo ohm, and we just need to evaluate the factor of R2, and both of these values supposed to be equal to 17.24. So now that after doing all this manipulation, you would end up having a result which is equal to 7.47, maybe 74.7 kilo ohm. Okay, so we got the value of R1 to be equal to 3k or 3 kilo ohm, and the value of R2 to be equal to 74.7 kilo ohm. Okay, and now here in this case, one has to re-verify the constraint. Okay, so the constraint states that the design supposed to have a value of resistor values that are lesser than 50k, but one could see here that the resistor value that we have achieved here basically goes above the value of this 50 kilo ohm. Now one way to constrain this particular result, or in order to work out this particular result, is by doubling the current. Okay, so rather than having the same aspect ratio for M5, what I can do is that I can just have the aspect ratio for M5 to be equal to twice the aspect ratio of W by L of P. Now when we do so, the current that flows through this M5 transistor will get doubled. Okay, so now in such situation, one would end up having the drop across this resistance to be returned as just twice I naught 2 into R2. Okay, and that is the voltage drop that we have. and over the other end the equations remains the same. The only thing is that just because we have this factor 2 that is appearing here, I could bring out this factor 2 to just be divided. Okay, so pushing this factor 2 towards the right hand side would ensure that this quantity to be, or the entire quantity to be divided by a factor of 2, or in short this factor of 17.24 would then be constrained by half the value. Okay, so hope that you're clear. So just by doubling, I'm just trying to reduce this factor of 17.24 to half of its value, and due to which when we try to do this manipulation, the R2 would then change from I think which would be equal to hope it is equal to 37.5 kilo ohm. Okay, yeah. So please verify whether you are getting the same result. In case if you are not attaining the same result, you can just uh, we can have a discussion in Zoom. Okay, so that is how we could able to reduce this factor by exactly half of this particular value. Okay, so nothing fancy about this results. Okay, just by doubling the width of our M5 structure, we can reduce the resistance value by further. Okay, so hope that you are clear with this problem. So today I have to begin with the other structure where one the the constraint that is imposed on the circuit, on this symbolic circuit, can also be realized by making use of one more structure, which is the second structure, by making use of the op amp. Okay. So whatever we discussed in the last class is by replacing this current sources with a supply independent biasing circuit, but now that I'm just going to use an op amp in combination with some resistors in order to realize those current sources, also to achieve the mechanism of VO1 to be equal to VO2. Okay, so let us see how does it work. So the BGR design using op amp. Yeah. So let me first draw the bottom structure where we have this VO1 as well as VO2 structure. Okay. And we know that this guy has to be realized with a diode connected structure. So in this case, I am reverting back from PNP transistor to an NPN structure, and one could still use the same PNP or NPN, doesn't matter, or one can even replace this diode connected structure with a diode which is forward biased. Okay. So here we have Q2, and this is n times larger than the emitter A of Q1, and this is what we have at the bottom. And in order to realize the currents with voltage VO1 to be exactly equal to VO2, one has to ensure a kind of negative feedback circuit that is tapping their outputs, tapping the inputs right away from the node VO1 as well as the node VO2. Just because we know that an op amp, and also we just need a combination of R2 as well as one more combination. Let me write this resistor as R3 here, and I need one more resistor in order to make sure that there is a current flow through the structure. Okay. So now what we are going to do is that we are just going to use an op amp. Let us consider this op amp is ideal, and let us try to create a negative feedback circuit by tapping the output of VO2 as input to the negative terminal, and the output of this is fed back to the resistor combination of R2 and R3. Okay, so hope that it is clear. Now this negative feedback will ensure that any voltage that I have here, which is basically VO2, has to be reflected onto this potential, onto this particular node. Okay, that is our that is how a negative feedback works when this op amp that we are considering is an ideal one. Okay, so whatever the potential that I have here will have to be reflected onto this, and this is how we have the discussion about virtual ground and all those stuffs, right? Yeah. So this combination of R3 and R2 along with this negative feedback across this A1 op amp will ensure that even this node will also be at VO2. Okay, so now we know that this particular node potential will be kept at VO2, and we also wanted this VO2 to be exactly equal to our VO1. So what we can do is that we can just connect this node, which we want it to be equal to VO2. Okay, so now the combination of this will ensure that it results in a value of VO1 to be exactly equal to VO2. Okay, so this combination or this requirement is basically provided by the negative feedback circuit created by the op amp and R2 and R3 resistor combination. Okay, so all of these things will ensure that our VO1 to be exactly equal to VO2. But the only thing is that where do we tap the output? Okay, so the output would generally be tapped at this particular node, which is taken as V reference, right? Yeah. So this is what we have across this particular circuit, and now we have to talk about the current flow through those resistors, right? So we need a potential to be fixed across this resistor R1, and in order to ensure that the circuit is also supply independent, which means that we don't want this R1 to uh, get sensed by any variation across our VDD. What one can do is that one can use this V reference output taken out from our op amp A1 is also being fed back to this structure. Hope that I'm not confusing you people, right? Yeah. So now that the combination of this op amp R3 R2 is just a kind of negative feedback circuit. Okay, and when we look carefully, one could see that there exists a negative feedback through the combination of R3 and R2, and where R2 is tapped towards or between the output and the input terminal of negative. Yeah, so this is what we have, and so in this case we had fed our value of VO1. Okay. So this particular op amp, if at all if it is ideal, will also ensure that our VO2 will be exactly equal to our VO1. Okay, and the output of this is taken as V reference. Okay, so now that let us try to talk about this op amp. So the type of op amp that we have realized is also said to be a non-inverting amplifier, and we know that the gain of this non-inverting amplifier, which is a closed loop gain, can be written as 1 plus the feedback resistor, which is in this case R2 divided by the R3 resistor, and this is the combination that we have out of this particular circuit. Okay, so V reference divided by the difference in this potential is said to have this. Okay, yeah. So or I can write it as closed loop gain. Yeah. So now let us discuss about how does this work and how would we ensure that everything works fine in the way that we want it, right? So now let us try to write the value of this V out or the V reference. So now, since because of the negative feedback, the V reference that I have here is also same as that I have it here. So I could write this V reference or the V out as something like a VB, which is the drop that I have across this particular circuit, and the current that is flowing through the resistor combination of R3 and R2. Okay. So the drop across this, so V reference or V out is nothing but the drop across the resistor R2 plus R3, because they are the same current flows through both the resistance value, I could write it as R2 plus R3 plus the VBE potential drop across Q2 structure, which I can write it as VBE3. Okay. So now we know that this, if at all, if our VO2 is exactly maintained at a value of VO1, one could write the current flow or the drop across this resistor R3. So the drop across resistor R3, provided if our VO1 is exactly equal to VO2, then one can write the drop across resistor R3 as VT into ln of N, and this we already know from our previous discussion. Okay. So this is the voltage drop, and in order to get the value of current that is flowing through this second structure, let me write it as IO2 here. The value of this IO2 can be retrieved just by knowing the drop across this resistor R3 divided by the resistance R3 value will give us this quantity. Now this current IO2 not just flows across this resistor R3, but it also flows across the series combination of R2 as well. Okay. So now with that taking into account, one can write the drop across the combination of R2 plus R3 as Vt into ln of N divided by R3, that is multiplied with R3 plus R2 plus VBE3. So it is not VBE3, VBE2. Yeah. So this V out or V reference is nothing but Vt into ln of N, and if I could able to bring this R3 term inside this R2 plus R3 combination, one would end up having a value which is 1 plus R2 by R3 plus VBE2. So now in this case, one could see that this combination of 1 plus R2 by R3 is nothing but the non-inverting amplifier gain, and that will act as a kind of alpha 2 factor for us. Okay. And due to a value of alpha 2 that is greater than the value of 1, the requirement imposed on this factor of N will also steps down. Okay. So in a way, rather than imposing this ln of N to have a value of 17.24, I am just imposing the constraint on the combination of alpha 2 times that of ln of N to have this 17.24. So now that if I choose a small value of N, the remaining quantity can be imposed on this alpha 2 factor, and that is what we have done with this both the circuit, okay, such that the value of N that I can choose can be small in this case, right. So we have finally done with the second type of circuit, which is made using the op-amp circuitry. And now that we just quickly do some problem in order to evaluate these resistance value. Okay. And there is one thing that I forgot to tell is that the unequal constraint, not just created by having a large transistor across Q2 than compared to Q1, one can also create the ln of N factor just by passing a different current densities or different collector currents through Q1 and Q2. Okay. Now let us do a simple problem wherein rather than imposing a factor of n with respect to transistor Q2, we just try to apply a different current densities or different collector currents across this Q1 and Q2 and trying to have the Q1 to be exactly equal to Q2. Okay, so one can also have that combination as well. So let us try to do the same with by solving a specific problem. So find the resistance So as you could able to note that we have a current value of IO1. In this case, I just wrote it as I1, which is equal to 80 microamperes. But the current density through the second branch is 10 times smaller. Okay, so which means that we have an n factor that is equal to 10 in this case when we divide these ratios. Okay, so in a way, just by having a different current factors, one can also have uh, the ln of n factor to appear. Okay, so hope that it makes sense here. Okay. And the value of VB1 is said to have 0.65 volt at 300 Kelvin. Okay. So now let us begin solving this by bringing out the circuit. Since because you have been given with two different current densities, we cannot apply the supply independent structure in order to create this BGR. Okay, but one can use the op-amp based BGR in order to create a different current flow through this branch 1 and 2. Okay, so it is only through this BGR design, which uses an op-amp, can support a different current flow through branch 1 and branch 2. Otherwise, when we use a BGR design that has been built by making use of supply independent biasing, cannot support a different current, okay, through branch 1 and branch 2. In that case, we have to work out with the n factor across the Q2 structure. We need to have a different area for Q1 and Q2 in those structures. Hope that it makes sense. Okay. So let me just copy this picture. So yeah, so now the current that is flowing through the first branch is given as 80 microampere, and the current through the second branch is given as 8 microampere. Okay. Now that we need to find all these values of R1, R2 and R3 combinations out of this particular circuit. And now we also know that our V reference is basically equal to 1.25 volt. Okay. So now based on this value, let us try to evaluate our resistor R1. Okay, just because the V reference not just applied for the second branch, but the V reference is also being applied across the first branch as well. So one could write this V reference as a drop across this resistance R1 plus the VB of Q1 transistor. right? And in this case, both our Q1 and Q2 can have the same area, and the factor n happens to have due to the different current flow through first branch and second branch, and due to which I can have the same area for Q1 and Q2 when you try to build a BGR out of an op amp. Okay. So with that being said, I could write this V reference as the drop across the resistance R1 plus the VBE of transistor 1, and already the VBE of transistor 1 is given, which is 0.65, and the V reference is equal to 1.65, and we just need to know the drop across the resistor. Okay. So the drop across the resistor is given by the current flow, which is I1 into R1, right? Yeah. So after doing a very pretty simple math, one would end up having this to be equal to 0.65 divided by the current, which is 80 microampere. So I guess this value will be closer to 7.38 kilo ohm. You please verify just because I'm not pretty sure about this particular value, right? Yeah. So now that we have this particular value for the resistance R1, and now let us try to evaluate the resistor value of R2. Okay. Now we know that whenever we use an op amp, this op amp, when it is in negative feedback, will ensure that the value of VO1 to be exactly equal to VO2, and the drop across this VO1 is nothing but, I could write it as V reference minus the drop across the resistor R1, and that's supposed to be exactly equal to our VO2. So one can also write this VO2 is nothing but V reference minus the drop across this resistor R2, right? Yeah. So in both the cases, we have this V reference. One could cancel those V references, and even the negative signs could be cancelled. So we end up having the drop across R1 to be exactly equal to the drop across R2. Now those drops are nothing but the current flows, right? So one could write it as I1 times that of R1 to be exactly equal to I2 times that of R2, and we know the value of both these currents, and in a way I could write this I2 as I1 divided by I2 into R1. So the ratio of I1 by I2, which is 80 by 8 micro amperes into R1, which we found to be equal to 7.38, will end up having a result of R2, which is equal to 73.8 kilo ohm, just because we have a factor of 10 being multiplied here. Now having done with this, let us try to evaluate the value of R3. Now the value of R3 is evaluated just by observing that the drop across this, or basically the drop across this resistor R3 basically mimics a PTAT circuit, and this PTAT circuit has the following requirement, right? That is the delta VBE, which is nothing but represents the drop across the R3 resistor, and that's supposed to be equal to Vt into ln of n. Okay, just because the current flow through both the structures of Q1 and Q2 are different, and they have a ratio of 10, the value of n that I have here is basically equal to 10. Okay, so we know this Vt at room temperature is basically defined as 26 millivolt, which I plug in here, and the ln of n could be written down here, and we also know the current value, which is I2, which is 8 microampere, and this simple calculation will give us the value of R3, and I guess the value of this R3 would be equal to 7.45 or 475 kilo ohm. Okay, so So we just solved a particular problem, and there are a few observations that has been done, and let me just summarize what we have discussed. Whenever we built a BGR using supply independent biasing, the currents of I1 and I2 will always be equal to same. Okay, so due to which the factor n can be realized only through the emitter areas. Okay, the BJTs emitter areas have to be different in that case. Whereas when we go for a BGR design using an op amp, in this case our I1 can be completely different from I2. Okay, so they can be equal, but they no need to have this particular spec. Okay, so it is something like I can have a different values of I1 and I2. In that case, the BJT's emitter areas can be equal. Okay, so this is a small bit of observation that you can use it. Okay, so hope that it is clear. So let me just try to end the stream, and I will send you the link of Zoom. You can just switch over to Zoom, and if you have any doubt, you can just ask me. Thank you.